First up, we have Jordan West and Cheng Wang of Netflix talking about how they've improved bad partition handling in Cassandra. They've done this kind of stuff at scale on Netflix, as you can imagine. And I'm sure some of you have probably read some of the use cases and case studies about it because there's some of that floating around as well. Jordan is an engineer at Netflix as well as a Cassandra committer. And Cheng is a database engineer at Netflix as well.
Hi, everyone. My name is Jordan West, and this is my colleague and coworker, Cheng. We're going to talk a bit about how we deal with bad partitions here at Netflix and some of the work that we've done over the last year to make dealing with them better in Cassandra. I've been at Netflix for approximately 2.5 years now. I'm a Cassandra committer. I've been a committer, or I've been working on Cassandra for about 7 years total, and with databases for a little bit over a decade. And now I do that at Netflix.
Hi, my name is Cheng. So I've been working with Netflix for about a year, a little bit over a year. I've been working on the Cassandra part. Before that, I've been working on the database domain for approximately 7 years in total.
Cheng and I both work for the online data stores team at Netflix. We provide data stores to pretty much the entire company as a managed service at scale, supporting pretty much all of the different business verticals, streaming, studio, gaming. And we also offer other stores besides Cassandra, as well as the underlying infrastructure and the clients that are used to connect to them.
So just give a very quick overview about the Cassandra, the Cassandra at Netflix. So right now we have over 22,000 nodes running at Netflix in prod, and with over 900 clusters with 12 plus petabytes of data. We have about 12 million plus requests per second. For the majority of the fleet, currently we are running on Cassandra 3.0x. So we are working on the Cassandra 4.1 and for production at Netflix.
A lot of the work we'll share here today is work that we've done in Cassandra 4.1 that's available, or in Cassandra or in Trunk, which would be Cassandra 5.0, and we've just either ported it or worked on it internally before open sourcing it.
Yeah, so the first question you may ask about it is why are bad partitions really bad? So this is one example showing our recent incident about caused by the bad partitions. So this graph shows the P99 rate latency. As you can see from the graph that during the incident window, the rate latency was pretty high, it's spiking up because of the bad partitions. So this is another graph showing from the application level. So as you can see that the bad partitions not only cause the latency from the Cassandra internally, but it also caused the latency spikes in the application level. So yeah, this is still the same incident, and it's give you another view of the replica rate for the due to the bad partitions. As you can see that even after we fail over from the application layer, fail over the traffic to another regions, from the Cassandra point of view, the replica read latency is still high, and it lasts for a few hours, which is unacceptable for Cassandra. So this graph shows you the access table the access table scanned per read for rate latency applications. We target for sub 10 milliseconds. The rate latency. So it's super critical to make sure that the number of reads, number of access table scan per read is small. So as you can see that during the incident, the time window, the access read, the access table scan per read is also spiked up, and it lasts for even days before we can fully mitigate the issue.
So bad partitions come in a few different flavors, some of which Cheng sort of highlighted in the incident he was sharing. They can be too large in total size. These typically present in the gigabytes plus size, even up to the terabyte size. That's not a problem that we have a lot here at Netflix just due to our workloads, but it is a type of bad partition that can impact Cassandra clusters. Another one is row count. So these may not be super large in terms of, number of bytes. They may be in the tens or hundreds of megabytes, but there are potentially millions of rows in the cluster or in the partition. And these millions of rows have processing overhead and it can cause problems. The same happens with tombstone count. So if some of those rows or some of the columns in those rows get deleted, as the number of tombstones increases, the problems from a single partition can increase as well. And the last one, which was highlighted in the incident, is the SS table count, and especially for latency sensitive applications, as Cheng mentioned, the lower SS table count is extremely important. And often they can come together. So you may have a lot of new rows introduced, which also introduces a higher SS table count because compaction's gotten backed up. And so it's not always just one of these, but it's at least one. And these have specific resource impacts on the cluster. So more CPU is used either to compact away these rows in the partition, to do merging, to process the tombstones. Memory usage is higher because Cassandra allocates a good amount of memory to read and load the data. That can lead to more buffer allocations, a higher object overhead, and more GC. Can also lead to reading more files, which means things like your page cache are thrashing or being used less efficiently, which can cascade down to the database. So either to compaction, slowing it down and reducing its effectiveness, which sort of exacerbates the issue, as well as read latency, as we saw in the previous graph. And that read latency can translate into application level errors. So we started to get a series of these, and we took a step back and tried to think about how we can make things better. And we break it down into 4 sort of areas that each build on each other. And the first is that we need to be able to identify what partition is bad. So this is actually not entirely simple in Cassandra, although it has gotten progressively better through the versions. But the first question that a customer may ask is like, which key is causing a problem? And so we want to be able to identify for them as fast as possible. And we'll focus on that first. The other ones are blocking the partition so that the reads don't affect the other partitions, and then mitigation. How can we make that partition not bad anymore? And then prevention. For identification, this was our status quo. We had a report. This report looks at a log message that looks something of the form writing large partition to key space table and then the key. So we were able to get the key. The problem is that this log message is logged on compaction. So there's no indication that that key that's listed there is the key that is causing the problem. So a bad partition can be lying dormant on disk, and while it may have a minor impact on compaction, it may not be the one that is being read that is causing the increase in latency that the user of the database is seeing. So we wanted to improve on this report and be able to get a real-time view as to what partitions were causing the problems. What we used to do previously, once we identified that partition by key, was we would find out what nodes owned it using get endpoints, find out what SS tables had it, and then we would do something like count how many rows with some like bash grep or using SS table metadata. But it was kind of like a hodgepodge of tools to get these answers. So finding which one was read and then finding why it's problematic was very, very manual, and not sort of like officially supported by the tooling. And we wanted to make that more of a first class construct in the database. So the first thing we did is specific to level compaction strategy, which is just to see which SS tables live in which leveled compaction level. This can be important because often one of the causes for increase in SS table count is level 0 or recent write SS tables. And because of that, it's nice to be able to use get SS tables -L instead of having to sort of piece this together from a bunch of SS table metadata and bash scripts, et cetera. So you can just do it with one call. And it also helps us identify how the partition is spread across the SS tables. So with get SS tables, you pass a key. And so now we can see if the partition is spread deep into the levels or at L0, and again, all in an official tool. This is included in Cassandra 18023 and will be in the next release of Cassandra. The other thing we did was to extend the profile load tool in Cassandra 3.0 if you're still running it. This is called node tool top partitions. But the idea is to look at which partitions are causing problems in real time, like we were talking about. And top partitions used to give us the top K by write counts. And what we added originally in 3.0 and then forward ported to profile load in open source was to track by latency, SS tables, rows, and tombstones. And you can find this work in Cassandra 18022. And these additional fields that were added to profile load will be included in the next trunk release of Cassandra. We also found an intermittent failure in top partitions that would often cause our operations, whoever was on call, to kind of be slowed down because top partitions would just return an exception. This doesn't affect folks who are using profile load as the code there has changed significantly. But if you are still running Cassandra 3.0.x, Cassandra 17254 corrects this issue. Basically, it was an incorrect use of the byte buffer API that led to these intermittent errors, this edge case. And again, this would slow us down pretty significantly, sometimes to the point where our team couldn't use top partitions at all. And so it was important for us to fix. Here's a quick example of how we use this. This is using the 3.0 top partitions because it's from a real production incident. So this is from our internal, like this is something I actually ran at one point. But in 4.1 and above, or in the newer releases of Cassandra, this would be profile load instead of top partitions. In the first one, you can see that we're getting a count of the tombstones that are there. And what was happening in this case is the customer had one partition that was extremely problematic. And they would get into the millions of tombstones and it would cause a cluster-wide issue. When this incident happened, the customer sort of suspected it happened and they reached out to our on-call, who happened to be me that week. And we were able to deploy this tool, which was new to us at the time, to prove to ourselves that this was happening. So successive calls to top partitions showed the max count for the started partition growing. And we knew that it was safe to delete many of those tombstones due to the nature of the application. So what we did, and this was our sort of standard procedure until more of the work that Cheng will talk about in a moment, was to alter the table to reduce GC grace seconds. So here we are reducing it to an hour, and then run compact, a full table compaction. And then as you can see afterwards, we ran the tool again. We can see the partition count go down immediately after, the tombstone count go down immediately after. It's not to zero because we set GC grace to an hour. So the 2,970 were tombstones that were written within the hour prior to me running compact. And we'll sort of talk about next, or in a minute, about why this is problematic and what we did to make it better. But in the meantime, this tool helped us in real time identify, without having to dump a bunch of SS tables and run some bash and run some grep and all those things, just able to run one command and prove to ourselves that our actions had been working, which when you're on call, that reduced friction is extremely important to us.
Okay, now let's talk about the blocking techniques we're gonna use. So now we got a list of like bad partition keys we're gonna need to block and mitigate it. So the block the partition block we do is like we backport the feature, like OSS feature called block list, which is also like deny list, which is like Cassandra 12106, which adds the ability to deny list a CQL partition. So all the requests gonna be ignored. So that feature enables us to prevent all the reads or range reads or writes which is like we can configure it's configurable like what is that we want for the given partition keys. Yeah.
And then one last thing to note here, if you are using the deny list, there was a bug that we found as we put this into production. If a node that was coming up was unable to do an initial load, it wouldn't have sort of the back off logic that it does once the node has done that first initial load. And this would lead to sort of like a thundering herd or storm on the cluster, which actually led to some incidents of its own. So we put the fix in Cassandra 18116 to prevent this issue.
Okay, now we have like identified a list of partition keys. We block the write to the keys. Okay, now the next step we're gonna do is to mitigate the issue, to get rid of these bad partition keys. So to do this, we develop a new tool called force compact. Okay, now, yeah, so this is like the new like node tool we developed recently. So the idea for the force compact is one, instead of compact a whole table, like the node to compact, we can provide a list of bad partition keys we would like to compact. So the idea is like when this compaction starts, it's only scans and the merge the SS tables containing these partition keys. And the next thing is like for the force compact is the idea for the force compact is it cannot ignore the GC grid seconds. Which is gonna like the keys. This is like the retention. We keep the keys. We know it's safe to remove the tombstone LTTL data. So we open source the new tool as Cassandra 17711 to the trunk.
And that'll also be in the next trunk release of Cassandra.
Yeah.
And this is an example taking from the previous example before.
Yeah, so this is like on the left hand side. So this is like what we did before we have the like Jordan described, like before we have the force compact, like we do the NT the node to top partitions, gets a list of bad partition keys, and then we do the alter table and set the GC grids to 1 hour and run the NT compact for the full table, right? So after once like on the right hand side, this is like how do we like do the bad partition keys mitigation. So like once we have a list of partition keys, we can just run the node to force compact for these keys, and instead of like setting the GC grids, and then all these bad partition keys gonna be purged. So,
and it's important to note here that the version on the left affects all of the data in the table. And also the node tool compact is an extremely expensive compaction that is different from the compaction that the Cassandra would run in the background. The force compact on the right, because as Cheng says, is targeted to specific keys, is significantly more efficient. In this specific case, it wasn't evident, but in other cases, the one on the left could take hours, whereas the one on the right takes seconds. Yeah. So this is an incident where force compact could make our life better, but there are also cases where force compact solved problems that we were unable to solve, specifically the topic of doomstones.
Yeah, so this is like one of the most recent incidents we are working on. So the problem is like there was like a data corruption issue, and that corrupted on the timestamp of the data, which marks the deletion info, which marks the type on the deletion as a future timestamp, which is we also referred as a doomstone data. As you can see, that the local deletion time is like 10 years old, like 10 years away. So in this case, like use a regular like NT node to compact would not work because we cannot set our timestamp to the future. And the problem here is like since the local delete time is future is set into the future, so any new writes for the same partition key gonna be marked as tombstone because we have the future deletion time, right? So for this case, we can just run the force compact, which gonna clean up this like doomstone timestamp without by ignoring the GC grids. So this is another use case the force compact is useful.
And this is where it's very valuable because, again, this was pretty much not an unsolvable problem before, but would require you to rewrite sstables by hand with custom code, or to throw the time of the machine, 10 years into the future, neither of which is relatively practical during a serious incident. So Cheng was able to use his tool to get us out of this incident relatively quickly, which is a huge win for us. So lots of uses for Force Compact for when you're going through production incidents. It's a dangerous but extremely helpful tool that you can use when you know that it is safe to remove those tombstones, either because your customer is not worried about the inconsistency, because repair has run, or a couple other conditions. Yeah. Thank you. This is some of the work that we've done to improve our handling of bad partitions here at Netflix. We didn't talk about prevention because that is work that is going on separately in the community. There's some work in the trunk to sort of improve the ability to support extremely large partitions. If you have any questions, you can reach us at the contact info below. We'd love to talk to you more about what we've done or incidents that you've had and how you could apply these tools to your fleet. Yeah.
All right. Cool.
Thank you.
Yeah. Thank you.
Thanks so much to Jordan and Cheng for that. Great to hear from you all, and thank you very much, everybody. See you next time. Bye.